Welcome to G Fun Facts Online. The dawn of 2026 has brought with it a palpable shift in the global energy narrative. For decades, nuclear fusion, the process that powers the sun, was dismissed as a scientific curiosity, a technology that was perpetually 30 years away. Yet, as we stand in the early months of this new year, that timeline has collapsed. The headlines are no longer dominated by theoretical papers, but by steel, concrete, and superconducting ribbons. The fusion age is no longer a distant dream. It is a burgeoning industrial reality. At the heart of this revolution lies a rivalry as old as the field itself, a technological divergence that splits the fusion community into two passionate camps. In one corner stands the Tokamak, the reliable, donut-shaped workhorse that has dominated research for half a century, culminating in the massive international ITER project and the agile private sector prowess of Commonwealth Fusion Systems. In the other corner, rising like a phoenix from the ashes of historical complexity, is the Stellarator, a twisted, chaotic-looking machine that promises the holy grail of fusion: steady-state, disruption-free power. The events of late 2025, particularly the record-breaking performance of Germany's Wendelstein 7X and the aggressive commercial roadmaps unveiled by companies like Proxima Fusion and Type 1 Energy, have fundamentally altered the landscape. The question is no longer just can we make fusion work, but rather, which machine will power the grid? In this episode, we are going to perform a comprehensive analysis of the physics, engineering, economics, and future trajectory of these two titans of magnetic confinement. To understand the rivalry between the Tokamak and the Stellarator, we must first grasp the Herculean task they are both trying to perform. The goal is to heat a gas of hydrogen isotopes, specifically deuterium and tritium, to temperatures exceeding 100 million degrees Celsius. That is 10 times hotter than the core of the sun. At these temperatures, electrons are stripped from nuclei, creating a state of matter known as plasma. The problem is that no material container can hold this substance. It would instantly melt the walls and cool the plasma, extinguishing the reaction. The solution is magnetic confinement. Since the plasma consists of charged particles, they can be trapped by magnetic field lines. Imagine a bead sliding along a string. The particle is the bead, and the magnetic field is the string. If you bend the string into a circle, or a torus, the bead can slide around endlessly. However, nature is not so kind. A simple circular magnetic field is insufficient. As particles travel around the torus, they experience a drift, caused by the curvature and the gradient of the magnetic field. Without intervention, this drift would cause the plasma to smash into the outer wall of the vessel in microseconds. To counteract this, the magnetic field lines must twist as they circle the torus, tracing out a helical path like stripes on a candy cane. This rotational transform averages out the drifts, keeping the plasma safely confined. It is in how this twist is created that the Tokamak and the Stellarator part ways. Let's look at the Tokamak solution first, which we might call the current of Sisyphus. The Tokamak, a Russian acronym for toroidal chamber with magnetic coils, was conceptualized in the 1950s by Andrei Sakharov and Igor Tamm. Their solution to the twist problem was elegant in its apparent simplicity. They used external magnets to create the main toroidal field, the long way around the donut, and then induced a massive electrical current to flow through the plasma itself. This plasma current generates a second, poloidal magnetic field, the short way around the tube. The combination of the two fields creates the necessary helical twist. This reliance on plasma current is the Tokamak's greatest strength and its fatal flaw. The strength is that it simplifies the engineering. The external magnets can be simple, flat, planar coils, which are relatively easy to manufacture. This allowed Tokamaks to scale up rapidly in the 20th century, achieving higher temperatures and densities than any other concept. The flaw, however, is that driving a current through a gas is inherently unstable. It acts like a lightning bolt trapped in a bottle. If the current is interrupted, or if the plasma becomes too dense, the magnetic cage can snap. This event, known as a disruption, releases all the stored energy in milliseconds, potentially melting the reactor walls and twisting the massive steel structure like a pretzel. Furthermore, because the current is typically induced by a central transformer or solenoid, Tokamaks are inherently pulsed machines. They must breathe, ramping up current, holding it, and then resetting. Now let's turn to the Stellarator solution, or the geometric web. The Stellarator, invented by Princeton physicist Lyman Spitzer in 1951, takes a diametrically opposite approach. Spitzer realized that you could create the necessary twist entirely with external magnets, eliminating the need for a current flowing through the plasma. To do this, the magnets themselves must be twisted and shaped in complex, non-planar geometries. Instead of a simple donut, the Stellarator looks like a cruller or a Mobius strip, twisted by a madman. The strength here is stability. Because there is no net current flowing through the plasma, Stellarators are immune to the violent disruptions that plague Tokamaks. The plasma is in a state of natural equilibrium. Crucially, because they don't rely on a transformer to drive current, they are inherently steady state. They can be switched on and run continuously for days, months, or years, which is a massive advantage for a power plant. The flaw, historically, has been complexity. The magnetic fields required are incredibly intricate. In the pre-computer era, calculating the shape of these coils was nearly impossible. Building them was even harder. Early Stellarators were leaky compared to Tokamaks, losing heat too fast because their magnetic fields weren't perfectly optimized. For decades they lagged behind, dismissed as too complex to build. However, the tide began to turn for the Stellarator in the 1990s and 2000s, not due to a breakthrough in physics, but a breakthrough in computing. The complex 3D magnetic fields that Spitzer envisioned could finally be calculated with precision. Optimization codes could tweak the shape of the magnets millions of times, searching for a configuration that minimized leaks and maximized stability. This era gave birth to the Wendelstein 7X in Germany and the Large Helical device in Japan. The Wendelstein 7X in particular was designed to prove that a computer-optimized Stellarator could match the confinement performance of a Tokamak. In late 2025, the Wendelstein 7X silenced the skeptics. While the machine had previously achieved long-duration plasmas of up to 8 minutes in 2023, those were low-density cruise mode shots. The fusion community was waiting for high-performance operation, the kind needed to actually generate power. The breakthrough came with a record-breaking 43-second pulse, where the machine sustained high temperatures over 40 million degrees and high density simultaneously. This achieved a triple product, the combination of density, temperature, and confinement time, that rivaled the best Tokamaks of similar size. It proved that Stellarators were no longer just stable, they were efficient. This 43-second shot wasn't limited by physics, but by the cooling capacity of the current hardware, which is a solvable engineering constraint, not a fundamental barrier. While Stellarators were maturing, Tokamaks were evolving. The disruption problem and the pulsed nature of the machine were not ignored. The International Thermonuclear Experimental Reactor, or ITER in France, remains the behemoth of the field. As of early 2026, assembly is progressing, with the massive central solenoid now fully integrated. ITER is designed to be the first machine to produce net energy, generating 500 megawatts of fusion power from 50 megawatts of input. However, ITER represents old-school fusion, massive, expensive, and based on low-temperature superconductors. It is a science experiment, not a power plant prototype. Its timeline has stretched into the late 2030s for full fusion operations, making it a slow-moving giant in a fast-paced race. The real excitement in the Tokamak camp comes from the private sector, specifically Commonwealth Fusion Systems. Spinning out of MIT, Commonwealth Fusion Systems leveraged a new material, high-temperature superconductors. These rare earth barium copper oxide tapes allow for magnetic fields much stronger than those in ITER, reaching 20 Tesla versus 12 Tesla. Physics dictates that the performance of a fusion reactor scales with the fourth power of the magnetic field. Doubling the field strength allows you to make the reactor 16 times smaller for the same power output. In early 2026, Commonwealth Fusion Systems is on the verge of activating SPARC, a compact tokamak the size of a tennis court that aims to do what ITER will do, produce net energy, but at a fraction of the cost and time. If SPARC succeeds in 2026 or 2027, it will validate the high field path and potentially allow Tokamaks to leapfrog the stability concerns by simply being small and cheap enough to replace easily. The commercial fusion industry has exploded into an ecosystem worth over $10 billion. The divergence in technology is mirrored in the business strategies of the leading players. Among the Tokamak leaders, Commonwealth Fusion Systems in the USA is the frontrunner. Their strategy is brute force physics via high-temperature superconducting magnets. They are betting that high margins of error provided by strong fields will make plasma control easier. Their pilot plant, ARC, is already in the design phase, targeting the early 2030s. Then there is Tokamak Energy in the UK, pioneering the spherical Tokamak, a cord apple shape that is more efficient than the traditional donut. They are also leaders in magnet technology. The Stellarator commercial space has gone from non-existent to vibrant in just 3 years, driven by the realization that utilities hate pulsed power. Proxima Fusion in Germany is a spin-out from the Max Planck Institute, the home of the Wendelstein 7X. In February 2025, they unveiled Stellaris, a fusion power plant concept based on quasi-isodynamic Stellarator physics. This is a magic configuration where particles drift in a way that naturally corrects itself, eliminating currents. Stellaris combines this with high-temperature superconducting magnets to shrink the Stellarator into a manageable size. Type 1 Energy in the USA is aggressively pursuing the brownfield strategy. Partnering with the Tennessee Valley Authority, they are aiming to build Infinity 1 at the site of the retired Bull Run coal plant. This is a masterstroke of strategy, using existing transmission lines and water rights to speed up deployment. Their Fusion Direct program utilizes the Starfinder optimization code to design magnets that are not just physically possible, but manufacturable. There is also Thea Energy, taking a radical approach by replacing the complex, twisted modular coils of a traditional Stellarator with an array of simple, flat coils that can be individually tuned electronically. This software-defined Stellarator could drastically reduce manufacturing costs. As we delve deeper into the engineering, the battle is no longer just about plasma physics, it is about manufacturing in materials. Consider the magnets, the heart of the beast. For the Tokamak, the magnets are D-shaped, planar coils. They are easier to wind. The challenge is the structural stress. The interaction between the toroidal field and the massive plasma current creates Lorentz forces that try to tear the machine apart. For the Stellarator, the magnets are 3D curves. Winding them is a nightmare of precision engineering. However, because there is no plasma current, the forces are more balanced and static. The challenge is pure geometry, fitting these twisted coils together with millimeter precision. AI-driven manufacturing and 3D printed casting molds have revolutionized this process in the last 24 months. Then, there is the divertor, the exhaust pipe of the machine where impurities and heat are removed. It takes the brunt of the plasma's fury. The Tokamak uses a poloidal divertor. It works well, but in a disruption, the heat load can jump instantly to gigawatts per square meter, vaporizing the tungsten tiles. The Stellarator uses an island diverter. The magnetic field naturally forms islands at the edge of the plasma. These stable islands guide heat gently to the diverter plates. Because the machine is steady state, the heat load is constant and predictable, allowing for better materials optimization. The breeding blanket is another critical component. Fusion requires tritium, a heavy hydrogen isotope that doesn't exist in nature. It must be bred inside the reactor by bombarding lithium with neutrons from the fusion reaction. For the Tokamak, the simple donut shape makes it easy to wrap a breeding blanket around the chamber. However, the blanket must be robust enough to survive the mechanical shock of a disruption. For the Stellarator, this is the Achilles heel. The complex, twisted shape of the vacuum vessel makes it incredibly difficult to design a blanket that covers enough surface area to breed sufficient tritium. Proxima fusion solution involves a liquid metal blanket that can flow into the complex shapes rather than rigid solid blocks. As we look toward the 2030s, the conversation shifts to the levelized cost of electricity and grid value. The Tokamak economic case is that they are the gas turbine of fusion. Proponents argue that their simpler build cost will always make them cheaper up front. Even if they are pulsed like a combustion engine, energy storage like molten salt thermal buffers can smooth out the electricity delivery. If a Tokamak pulses for 2 hours and rests for 20 minutes, a thermal tank can bridge the gap. The Stellarator economic case is that they are the hydro dam of fusion. Proponents argue that the cost of electricity is driven by availability. A Tokamak that shuts down for maintenance frequently due to disruption damage or has to cycle its stress regularly will have a lower capacity factor. A Stellarator, running steady state for months, provides true baseload power. Utilities, they argue, will pay a premium for a machine that never blinks. Furthermore, the lack of disruptions means lower safety margins are needed for the building, reducing the nuclear concrete cost. The retrofit opportunity highlighted by Type 1 Energy's project at Bull Run highlights a massive market, retrofitting the world's 2,000-plus coal plants. These sites have the steam turbines, the cooling towers, and the grid connections. A Stellarator, which operates as a steady heat source, is a perfect drop-in replacement for a coal boiler. A pulsed Tokamak is much harder to integrate into a steam cycle designed for constant pressure. In 2026, no one builds a fusion reactor without building it in the virtual world first. We are in the digital twin era. AI tools like StelFoundry and Starfinder have reduced the design cycle of a Stellarator coil from years to weeks. They optimize for coil complexity, penalizing shapes that are too hard to bend. Commonwealth Fusion Systems is partnering with NVIDIA to create a full digital twin of SPARC, allowing them to simulate every bolt and wire. For Stellarators, digital twins are even more critical to ensure that the complex parts will actually fit together during assembly. Looking at the road to 2035, the next decade will be the filtering phase. From 2026 to 2028, SPARC attempts net energy, and the Wendelstein 7X completes high-performance campaigns. First prototype Stellarators like Infinity 1 will break ground. From 2029 to 2031, we expect the first fusion pilot plants to come online. These machines will generate electricity for the grid, likely in the 50 to 100 megawatt range. By 2035 and beyond, we see commercial rollout. The likely outcome is a split market. Tokamaks, being further ahead, will likely be the first to put electrons on the grid, serving as peaker plants or industrial heat sources. But as the grid becomes saturated with variable renewables like wind and solar, the value of the Stellarator's rock-solid, steady-state profile will rise. By 2040, the Stellarator may well become the workhorse of the decarbonized baseload, the true successor to the coal plant. The Stellarator versus Tokamak framing, while dramatic, is ultimately a story of synergy. The high-temperature superconducting magnets developed for Tokamaks made the Stellarator compact. The plasma physics learned in Stellarators is helping Tokamaks control their edges. In 2026, humanity is no longer betting on a single horse. We have a stable full of thoroughbreds. The Tokamak is the muscular sprinter, ready to burst across the finish line of net energy. The Stellarator is the marathon runner, pacing itself for the long haul of powering civilization. For the first time in history, the question is not if we will have fusion energy, but which flavor of star we will choose to bottle. The answer, likely, is both.